Hello, this is Jonathan, and I'll be going over the localization pipeline. How we go from this image on the right to essentially figuring out where the robot is located on the field. Okay, and so just for a preview of what's to come, I'm going to go over the code on how we take this, going back to this image from the simulation or from the real life, and we do some movie magic or just, computer vision. We apply some computer vision libraries so we can isolate the lines. Um, we can isolate the lines and turn them into these white and red points here, these point clouds and laser scans, so that we can actually use those as reference to figure out where we are on the field. Okay, so let me take you to the code. Here we are. Okay, so all this code is located in the Soccer object localization. And we'll be going through all of this through detector field line and so on. So for detector field line, um, essentially it's all the magic happens here in image callback. So after we get an image from the simulation, this is just some boring stuff to determine do we want the camera to be turned on? Is it ready to actually give us some data? Okay, and here. So we take this image. So this is us taking an image from the input into this function. Then we calculate the cover horizon. The cover horizon sounds like just kind of a fancy name for we're going to draw a big rectangle based on the camera geometry, the camera angle, so that we don't see above the grass field. Because if we do see above the grass field, or a little bit above it, we'll see in like a real competition, we'll see noise, we'll see other people's shirt, and that might cause some errors for the robot. So it's just better to block out all the unnecessary noise. And we yeah. So the first thing so after that we convert from an RGB or a BGR to an HSV, which is like RGB, but essentially it's better for determining the different types of color. It's better for determining and isolating different types of color, essentially, which is very important because one of the first things, and just this is it doesn't really matter. Yeah, it's just a mask that we're going to use to define how we want to isolate certain things. So we're going to take this image, this green image. We yeah, we convert it to HSV, and then based on some of our own experimentation, the first thing we need to do is creating we need to get rid of all the grass essentially because we only want the lines because that's our overall goal. We want to look at the lines and be able to accurately get them, but there's a lot of other stuff, and the first thing is the grass. So if this we essentially we're able to remove everything but grass since it has a very unique color intensity. Um, yeah, we're able to remove everything but the grass. Then we go on to essentially kind of grayscale the image so that we can better isolate the lines. And then essentially this whole process with the morphology EX, the whole overall process of like this 6 lines, and it does look a little bit daunting and confusing, but it's all in the library. We're just looking for different functions on how to apply different things. And essentially, what we're doing is in the end we're trying to get really great lines. So the first thing that we do with this Murph close, this actually line isn't used more for testing, is this essentially removes the holes inside the lines. Let me get a quick example. Yep. Here it is. Here's just the Wikipedia, not the Wikipedia, but this is like documentation. So we use something called closing, which essentially it will take this noisy line that like so this eye has a bunch of dots in it, and that might interfere with us detecting lines and this thing is just a great way of closing it and making it open. And so yeah, that just removes the whole line so that there's less noise. And then this one opening, which we use afterwards, just essentially gets rid of all the white dots, the noise outside of the lines that we're trying to get that might be misinterpreted for lines. And actually, if you look here in RViz, we're still doing it, so there maybe is some improvements that we need to do here based on the lighting. Yeah. So this essentially, we're looking at the lines and we're trying to make them robust and stronger so that lighting and just angles don't, so that we can still get a lot of line data for what we need. A road is sort of the same. A road essentially just removes a lot of the boundary lines. It's just not a process. Anyway, moving on. So after we got an image with really good robust lines, we can do stuff with it. So we flip here because we're taking the original image, grass only, because these were like we created new ones. Um, Before we did any of the morphology to get the better lines, and we flip it, and bitwise knots essentially just flips all like black to white, white to black. It's yeah, and then we can do a bitwise and, which essentially is combining both based on a mask. So it kind of looks at this image and says, I only want to get the lines. I don't care about anything else. I don't care about the grass. I don't care about anything else other than the lines. And I want this to be the only thing in our image, more or less. Um, yeah. And then after that, we do another, morphology EX to like a more close, so that we can get even more accurate lines. Um, yeah. And like a lot of this like morphology, just because I might have gone over it, it's just really repairing the lines so that there's not a lot of noise, more or less. Okay. After that, so we've gotten our line. We got an image with lines. Now the hard part. So we got the lines, but we need to feed this into our localization algorithm. And essentially, we take these lines and we split them up into points. It's kind of mostly over here. It's a simple for loop. We just simply take a line. We go every 30 odd distance. I want to take this point, this point, this point. Um, yeah. So after we split the lines into points, we transform them using the transformation library. Because essentially we found out that we found a line, but we only know its pixel. Like this pixel is like 640 by 480, or so on. And that doesn't actually help us in knowing where that is in the world, because it's only known in the camera view. So we have our own library to essentially convert the pixel. I don't want to get too much into it, but essentially we do a projection of our pixel based on on the location and the height of the camera. We can do a projection on the pixel to the real world, to the floor coordinate, so that we can actually use this point in the real world, so that we can actually have a good distance of things. Okay, and then after that, it's simply just we publish this as a point cloud to something called laser scan, which I will get into. So here's something that we might have not shown in the past. Is this the one I want? No. Okay. Rqt graph. We know that says Qt. There's actually an R. Just weird some things. Okay, so it will make this very complicated. But this essentially, these are all the nodes and topics that the robot is currently using. And so just to iterate that point, like we have robot state, so technically it should be from camera. I mean, actually we do. So technically we have the robot camera, so this could be the physical web camera from the simulation. We give it input into the detector field line, which does the processing, and then using this topic field point cloud, we send that point cloud that was extracted from the image to point cloud to laser scan, which is a library we found that just simply converts it into a laser scan, which is necessary for AMCL or sorry, uh, forgot. It's AMCL is uh, Monte. It's like Monte Carlo localization. Essentially, we use a ROS library to take in laser scans, to take in the odometry, which is just like where we think we currently are based on how far we've walked, and the IMU, which is just a sensor that tells us our general direction, more or less. And we use all this to and we plug this all into AMCL, which is a probabilistic algorithm that tells us the biggest probability of where we are through AMCL pose. And that's like a really um, high level overview of what that is. But also I want to show, like going back to how, this kind of whatever. Um, this is just the line that we extracted, very strong, clear lines, but there's still lots of things to do. And yeah, and we can see that as well. So these are pretty good lines, but there's still some more or less problems that we can still fix and improve upon. But it's more than enough to be decently accurate. Accurate. Um, Quickly, just like detector goalpost is the exact same, more or less use the same algorithm, though it is on a slightly older version. And never mind, I was trying to do something else. Okay, going in more onto AMCL. Let's see. So for AMCL, it's pretty much we just plug and play with a few different things, but I'll show it in work in here. Um, so I'm just gonna put a, here, I'm gonna give a nav goal like over here. And so it's gonna start walking. Hope it doesn't fall over. And it's hard to show from my angle, but you can kind of, not really that well actually. You can kind of see like these really, uh, you can sort of see. Well, you can't actually. I'm just gonna do this. Okay, there we go. So I just did a DD pose estimate. That's to say I'm telling the robot is here for initialization purposes. These green arrows are the probabilities clustering of the most likely where it is. Let's see, I'm going to give a pose. And so as it walks more, and oh yeah, this purple um, circle is the covariance. Essentially, it's like the probability of it thinks it's somewhere in the circle. And the greens are better estimates of where it thinks it is. And so it's pretty accurate because it's very clustered right now. And sometimes if we give it a giant walking thing, sometimes based on the line data, based on different offsets, it will be inaccurate. Sometimes it'll just teleport randomly. But that's more or less AMCL, probabilistic algorithm that we feed in a lot of IMU, odometry from where it's gone, laser scans of the map, and it's always trying to compare the current laser scans to where it could be on the map. Um, and it then it spits out where we think we are on this map that we give it. And that's essentially that is what localization is, from input getting the image and outputting it. Um, yeah, there's a few things I do want to show, like where in the launch file. So this is localization at launch. It's in Soccerbot and then launch and then modules in the localization.launch file. So it's like this is where we have everything. Um, all the nodes like robot EKF, which merges. So it's using something called extended Kalman filter. You don't need to know the details, but essentially it merges odometry and our IMU to get a better accurate idea of where we are. And then IMCL is just down here at the end. Um, that's not much of note, but then we have AMCL, the YAML, like these, we have all these YAMLs that determine how our AMC algorithm will run. The amount of particles, because the more particles is more computational heavy, and sometimes we just can't run that much on some weak and old hardware. And it kind of goes on. There's different models for the laser beams, for the even the type of odometry, and this like library is not great because this is meant for wheeled robots, whereas we're a humanoid one. So we got to really slowly do it as well. Yeah. And so there's some other stuff. This is like EKF map. It's just showing a bunch of how we want to configure it. It's not that important. Yeah. Some other really important stuff to know about the localization is how it interacts with ROS. No, how it interacts. Yeah, how it interacts with the strategy and the control systems, because there's a lot of interaction there. So if we go to soccer, let's start with where I am, I guess. So applying head rotation, our localization is really, really reliant on our head, because if it goes too fast, then it won't localize properly. Well, like taking snapshot images, maybe they'll be blurry or it won't just get enough of the details. So applying head rotation is massively important, and it's located here in Soccer Pi control and Soccerbot ROS at the end of the file, and it's quite complicated. That's for another video. And then how it interacts, how localization as a whole interacts with strategy. It's located in Soccer Strategy inside Robot Control 3D through, yeah, sort of every here. So it's here AMCL callback, so it will make sure that we keep on every time we get an AMCL pose, it'll also make sure are we good enough? Is the probabilities, the covariance of our location actually small enough, or do we need to keep on localizing, or because if we don't know where we are, why should we take an action? More or less. And it's really just publishing like are we localized, and also how recent is the localization. That's mainly it for those. Something I do want to bring up is TF more as a whole, because we do bring it up every once in a while. Uh, Give me a second. So, yeah, this video is running along, but essentially for TF transform. So actually, it's probably best from RViz, if only I had a better control of it. Just one. Hmm. Okay. Third person follow. There we go. Okay. If I localization robot model. Okay, let's remove robot model. So transformation is honestly just a fancy. It's a whole field of study, but it's sort of it's multiple different corner frames, frame of references. So you have your frame of reference for the world as itself. You have a frame of reference in respect to where the robot is, like, and then you have like where is the robot inside the world. That's something easy to understand. But then there's stuff like the ball. It's both important to understand where the ball is in respect to the robot, because that's how far we need to go, and also where in respect the ball is in the world, because then other robots can know exactly how they're far away from. So these are both all important things. And so in a robot, you can see there's different frames here for because each frame of reference, the bicep, the forearm, the calf, the ankle, we can using transformations, we can figure out what's the distance, what is the actual exact position of this in relation to everything else. And this is very important in the field of robotics. Um, Something I want to show. I'll remove that. and add in Rqt. Okay, yep, here it is. Yeah, okay. This is called Rqtf Tree. I don't know why I said okay. And essentially it shows how everything's connected. So this we can see all the transformations. We can see how the torso goes to the neck, but not necessarily the neck goes to the hip, because it's a tree. And so we can see how technically you can see where the ball is. This is like GT means ground truth, so technically we don't even see the ball in here. But what if in the simulation, I put the ball right in front of it? Let me just make sure it's actually detecting it. There we go. It's detecting the ball. Now if I open up the Rqt graph and then I refresh in the right here, I got ball now. It now sees the ball. It's now in part of it. So technically, and even if, and here's another one for TF and how. Oh no, I don't want to do that. Okay, for TF tree is because we can do Ross run TF echo world robot one. It's if you ever need any, just ask us because there's just a lot of information. But we can find exactly where in the world it is for robot one, and we can see in the world it's at minus 3.4, 1.3, in rotation. Or we can find out where it is with, base. No, I can't. Okay. Footprint. So where is the ball in respect to the robot? And we see, so before it was 3.4 and 1.3 in the world. Now it is 3.4 and 0.4 because it's just in front of us. But why? We're kind of looking exactly at it. And just to bring this more into respect, we can see if this would line up. That this is the ball, the robot ball, and it's in the sort of frame of the robot. And so if let me go back here, put this down here. If I move, so I'm moving it in. You can see on the camera on the left, I'm moving it in here, and it's changing in here, and that's all sort of connected with TF. And so TF is very useful for like a lot of things. If we want to make sure, do we see the ball? Do we see other robots? Is our camera actually, looking above us or in place? These are all important questions to know in a game, in a soccer ball, in a soccer match. Anyway, I think that's been enough time. I think this has gone on long enough. But this is the localization pipeline from image to execution, I suppose.